Okay, so welcome back to this next video in which we are discussing conjugation in the symmetric group on the set of n elements. Okay, right, so we've just been discussing the cycle decomposition of a set permutation, and the example we did was a set permutation on the set of 8 elements. Okay, what I'd like to do now is give you another example of cycle decomposition of a set permutation, this time on a set I think that's slightly smaller, and then what I'd like to do is use this to lead into a discussion of what it means for two set permutations to have the same cycle type. Okay, and then what we're going to do is we're going to use this concept of two set permutations having the same cycle type to arrive at what happens when you conjugate one element in the symmetric group on the set of n elements by another element in the symmetric group on the set of n elements, and what it can actually be interpreted as meaning. Okay, right, so that's where we're heading. So firstly, let's have a look at this other element that I'd like to have a look at and do the cycle decomposition of. So we're going to downsize a bit. So we just did a set permutation from the symmetric group on the set of 8 elements. Let's now downsize to the symmetric group on the set of 5 elements. 5 is big enough that I can illustrate the point that I want to illustrate, and it's a nice size that isn't too long-winded to draw out. Okay, right, so we'll do S5. So let me make a set permutation then of the set of 5 elements. So here I'll draw out the set of 5 elements here, and again I'm going back to drawing it in numerical order, but of course I will, once we've done the cycle decomposition, write it in a better order to make the set permutation look simple. Okay, so initially my set permutation is going to look complex, but we're going to simplify it once again using cycle decomposition. So let's say we'll send 1 to 4, okay, we'll send 2 to 5, okay, let's send 3 to 1, let's send 4 to 3, and let's send 5 to 2. Okay, so again we've got a total mess there. It looks horrible. Okay, it looks horrendously complicated. Okay, but let's do the cycle decomposition of this and decompose it into much simpler set permutations on subsets of this set of 5 elements, namely cyclic set permutations. Okay, so once again, we follow the same algorithm, and I'll just make sure this is in view of the camera. Yep, it is. Okay, so we'll start off with number 1 here. Okay, the smallest number. We'll open the first cycle, start with number 1. Okay, and 1 is sent to number 4 here, so we send 1 to 4. 4 is sent to 3, so we'll put a 3 there, and then 3 is sent to 1. Okay, so we close that cycle there. Then the next smallest number in the set that isn't already in a cycle is of course 2 here, and 2 is going to be sent to 5, so I'll put 5 there, and then 5 is sent to 2. And now we've got all of the elements of the set of 5 elements in cycles now, so here is the cycle decomposition of this element of S5 here. Okay, and clearly this doesn't have any 1 cycles, but if we did have any 1 cycles, we'd have to get rid of them. Okay, right, so there we have our cycle decomposition of this element of the S5, and what this allows us to do then is interpret this set permutation of the set of 5 things as in a much simpler way, as the composite effectively of these two cyclic set permutations on these subsets of the set of 5 elements. So what I'll now do is just rearrange the way that I write the elements. So I'll now write this 1, 4, 3, 2, 5, like so, and again down here 1, 4, 3, 2, 5, and now I can rewrite this exact same set permutation like so. 1 is being sent onto 4, 4 is sent onto 3, 3 is sent onto 1, okay, so a nice 3 cycle there. Okay, 2 is going to be sent onto 5, and 5 is going to be sent onto 2, a nice 2 cycle there. Okay, so here then is my set permutation written in this nicer way. Okay, so that's then another example of taking the cycle decomposition of a set permutation. Okay, now I said I had something new to say, okay, and to say my new thing, I'm going to draw up come up with a new set permutation, and I want to compare this new set permutation, which will be a different set permutation to this one that I've got here, to this one, and I want to see the similarities between it, and that will lead us to an understanding of what it means to say that two elements, two set permutations are of the same cycle type. Okay, so let me draw out this other set permutation here. So once again, here's my set 1, 2, 3, 4, 5, and again here 1, 2, 3, 4, 5. Okay, and then this new set permutation that I'm going to draw out is quite simply 1 will be sent to 2, 2 will be sent to 3, 3 will be sent to 1, 4 will be sent to 5, and 5 will be sent to 4. Okay, now hopefully you can see that there is some sort of similarity between these two set permutations that I have got here. So I have this one highlighted in red here. So I've got two set permutations that are fundamentally different. Okay, this is not the same as this one here. Okay, it's sending elements of this set to very different elements of the set than this one does. Okay, but looking at these two pictures, comparing this picture of this set permutation to this one, we can see that there is some similarity between these two. Okay, now let's do the cycle decomposition of this set permutation here. Okay, so this is again good practice. So 1 is sent onto 2, 2 is sent onto 3, and then 3 is sent onto 1, so close that cycle, and then we've just got the 2 cycle involving 4 being sent onto 5 and 5 being sent onto 1. Okay, so again, the cycle decompositions here look very similar, these two things. Again, you can see the parallels. Okay, and to make this even more firm in your head, what I want to do now is draw out another set permutation that is not similar to these two at all. Okay, so let me draw out another one here. So I have the set 1, 2, 3, 4, 5 here, 1, 2, 3, 4, 5. Okay, so here is this other set permutation. So it can swap 1 and 2 around, it can swap 3 and 4 around, and it can send 5 onto itself. So here is our fifth set permutation of this set of 5 elements, another element of S5 here, and I'll highlight this one in purple. And let's take the cycle decomposition of this. So this will send 1 onto 2, and I almost put a comma there, but managed to stop myself, and then it will send 3 onto 4. And then we won't put that 5 is sent onto 5 because the standard way of doing it is not to put 1 cycles. Okay, so we can see that this element that doesn't look anything like these two has a very different cycle decomposition to these two. Okay, right. So now let's explicitly say what the similarity between these two set permutations that I've got here actually is. And it is that the arrows are pretty much the same, basically. If we take the cycle decompositions of these two elements, this one consists of a 3 cycle with a 2 cycle, and this one also consists of a 3 cycle with a 2 cycle. Yes, the cycles involve different elements, but the types of cycle that you have here are the same. Indeed, if I cover up the numbers here, if I put my fingers over the numbers, these two look exactly the same. The arrows here are the same. The structure of the set permutation is the same. Okay, so this is what we mean by cycle type. Okay, we would say that these two set permutations, although they are different, they have the same cycle type. Their structure is the same. They consist of a 3 cycle with a 2 cycle. Okay, so this is the concept of a cycle type. It means that they have the same combination of lengths of cycles. So they have the same number of cycles of each length in their cycle decomposition. That is what is meant by set permutations having the same cycle type. This set permutation down here, meanwhile, is not the same cycle type as these two. Okay, if I cover the numbers up here, those arrows look very different to what I've got here. This one is a different cycle type. Okay, when I take its cycle decomposition, it has differing numbers of cycles of each length to these two. Okay, so that is what is meant by two elements of the symmetric group on the set of n elements having the same cycle type. Okay, now what we want to discuss is conjugation in Sn, and believe it or not, the concept of two elements having the same cycle type is going to be so important. And in fact, the way we're going to arrive at conjugation in Sn is by exploring these two elements that have the same cycle type in even more detail. Okay, so what I want you to consider is that I could turn this set permutation here in green into this one, okay? This one with the same cycle type as this one, simply by relabeling up the elements of this set of 5 things. Okay, and what do I mean by relabeling up? I mean changing the symbols here, saying, okay, I don't want 4 anymore to be called 4, I want it to be called something else maybe. Maybe I might like to call it 2 instead. Maybe I'd like to replace this symbol with the symbol for 2. And if I replaced this symbol in both sides here, okay, so both in the domain and the codomain with 2, okay, then I'd be getting this one closer to this one, okay? Similarly, what I want to do down here is I'd want to send 2 onto 4, so I'd want to relabel up 2 here with 4. So I'm saying just change the symbols here. Say, okay, I don't want to use this symbol in this position anymore, I want to use this symbol in this position. And again, I don't want to use this symbol in this position anymore, I want to use this symbol in this position anymore. Okay, keep all the others the same, and can you see that if I just relabeled up the symbols in that way, I would turn this one into this one. Okay, so just by relabeling up the symbols in the domain and codomain of the set permutation, I can turn this set permutation into this set permutation because they are of the same cycle type. Because when I relabel, all I can change is this bit. Okay, and I'll highlight this up. When I relabel, all I can change is this bit and this bit. I cannot change this bit. Okay, the fundamental structure of the set permutation, this combination of arrows, I cannot change. Okay, so I can turn it into this one because this one has the same combination of arrows here. It just has different this bit here and different this bit here. So by changing these two bits, I can turn this one into this one because the arrow structure is the same. I cannot turn this one into this one just by relabeling up these symbols here because the arrow portion, the fundamental structure of the set permutation, is different there. Okay, right, so that gives us a deeper meaning to what it means to have the same cycle type, that the fundamental structure of the set permutation is the same. These two have the same fundamental structure. They're slightly different in what elements they're actually sending where, but their fundamental structure as a set permutation is the same. So cycle type is a very deep characterization of a set permutation. Okay, right, so now what I want to do is explore this concept that we can relabel up these elements of the domain and codomain of a set permutation and turn it into another one, okay, because this turns out to be what conjugation is going to actually mean in the symmetric group on the set of n elements. Okay, so let's go on to the other side of the paper here. Okay, right, so let's draw out this set permutation again, and I'll have to just probably go back to remember. I think it was 1, 4, 3, like so. Okay, and then 2, 5, if memory serves correctly. Okay, and then 1 was being sent on to 4, 4 was being sent on to 3, 3 was being sent on to 1, and 2 was being sent on to 5, and 5 onto 2. Okay, now more generally, because I want to go more generally, I don't just want to consider this one example. Okay, more generally, I am going to call this set permutation that I've got here sigma. Okay? And what I'm now going to consider is trying to change this set permutation by relabeling the elements of the domain and the elements of the codomain. Okay, so I want to turn this set permutation into another set permutation that we now appreciate will have to have the same cycle type as it through one of these relabeling maps. Okay, so this relabeling map here, let's think about it in a little bit more detail, and I think to actually think about it, I will actually do the concrete example that we had, okay? So the relabeling map we had here, all we were going to do was take 4 onto 2 and 2 onto 4. Okay, so I'm just trying to decide how I'm going to draw this out. I think I will go back to having the elements of the set written in numerical order here. Okay, right, so let's think about what I want to send everything onto. So I want to send 1 onto 1, so I want to keep 1 exactly the same with this relabeling map. I want to send 4 onto 2 here. Whoops, I want to send 3 onto 3, so I'll just take that arrow over there. I want to send 2 onto 4 here, and I want to send 5 onto 5 here. So all I wanted to do was swap around 2 and 4 here, okay, which indeed I've done now. Okay, and I know this looks like it's an identity map, but you have to bear in mind that I haven't written this in the same order as I have here, so really this is swapping around 2 and 4. Okay, and of course I need to do the same relabeling map over here, so I'll draw out my numbers again. So 1, 2, 3, 4, 5. I want to send 1 onto 1, 4 onto 2, 3 onto 3, 2 onto 4, 5 onto 5, and again I'll stress that although it looks like an identity map, it's not, because the order I've written them here is not the same as the order I've written them here. Okay, so let's call this relabeling map that I've got here tau. Okay, so this is my tau relabeling map, and because it's a relabeling map, what do we know about tau? And I'm sorry this is on an angle, okay, I'll just straighten it up. What do we know about tau because it's a relabeling map? Well, the key thing that we know about it is that it's going to be a set permutation of the set of 5 elements in this case, but more generally on the set of n elements. Okay, so because it's this relabeling map, it has to be a set permutation of this set of 5 elements. Okay, so tau is actually going to be an element of the symmetric group of 5 elements. Okay, because remember this contains all set permutations, and any relabeling map is going to be a set permutation. Okay, more generally tau will be in the symmetric group on the set of n elements. Okay, now let's ask the question. The new set permutation that we create once we have relabeled up the elements of the domain and codomain in this way, what is it actually going to be equal to in terms of tau and sigma? Okay, well the new set permutation is going to be the set permutation that maps this thing, this set here, all the way over here, and I hope you can understand that. Okay, so here in the middle, sigma here, was our original old set permutation. We are now relabeling up the elements here, and the new set permutation we get will be a mapping from this new relabeled up domain here to this new relabeled up domain here. And overall, what now is that mapping? Well, it's the mapping that firstly does the inverse of tau, then does sigma, and then does tau forward. Okay, so we need to go backwards here. We need to invert tau here and send it the opposite way. So we need tau inverse, then we need to do sigma, and then we need to do tau. So this new mapping is going to be firstly tau inverse, and remember when you're listing the order that mappings are going to be done in, it's done in the counterintuitive way. So tau inverse is going to be on the right here, then we do sigma, okay, and then we do tau. Okay, and now you should be shuddering. There you go. What does that look like? Okay, well that looks like conjugation. Okay, and here at long last then we have some sort of an interpretation as to what conjugation actually means. Okay, so let me make this utterly explicit then. Okay, so tau was an element of our symmetric group on the set of n elements, and I'm now going to generalize, so we'll go on to the set of n elements rather than just staying with the set of 5 elements. Okay, so tau was an element of the symmetric group on n elements. It was a relabeling map that was telling us how to relabel up the elements of the domain and codomain, okay, and sending them on to something else, which was a set permutation. And you could have used any of those set permutations you like to relabel up the elements of the domain and codomain, okay, and get a new set permutation overall. We use this specific one because remember we were trying to turn it into this one here, okay. Then sigma again was some arbitrary element of the symmetric group on the set of n elements. Okay, and I am saying that if you want to change sigma by relabeling up the domain and codomain according to the set permutation tau, which is being viewed as this relabeling map, Okay, the new mapping that you will get, which will be of the same cycle type, because you don't change this bit here, all you change is the domain and the codomain. Okay, the new mapping that you get will be of this form, tau, sigma, tau inverse, i.e. this is the meaning of conjugation of one element sigma by another element tau in the symmetric group on the set of n elements. Okay, what it means is we are changing this element sigma by relabeling up the elements of the domain and codomain according to this relabeling map tau, and we will get some new elements of the symmetric group on the set of n elements, some new set permutation, but that set permutation must have the same cycle type, because I've just shown you the intuition behind what this means. Okay, so that's what conjugation actually means. And just to show you that this actually works, okay, let's actually work out what this net mapping is and show that it is equal to that thing that we were trying to get. Okay, so I'll draw out my new mapping. So we're going to be mapping from 1, 2, 3, 4, 5 to 1, 2, 3, 4, 5, and we're mapping from here to here, the relabeled up domain to the relabeled up codomain here. So where's 1 going to go? Well, 1 is going to go the inverse of this. We're going along backwards here, so we'll go back to 1 here, then it will go to 4, and then it will end up going to 2. So 1 will go to 2. 2 will go backwards along here to 4, then it will go along this way to 3, and then it will go to 3. So 2 goes to 3. 3 will go backwards along here to 3, then it will go to 1, then it will go to 1. So we'll end up with 3 going to 1. 4 will go backwards along here to 2, then it will go to 5, then it will go to 5. So it'll go here. 5 will go backwards along here to 5, then it will go to 2, then it will go to 4. And there you are. That was exactly the set permutation that we were trying to turn this one into, basically, through this relabeling map. Okay, so by relabeling up the domain and the codomain, you can turn this element into another element of the same cycle type. And what does that actually correspond to doing? It corresponds to conjugating this element by some other element of the symmetric group on the set of n elements. Okay, and where that other element is being viewed as this relabeling map. Okay, which is relabeling up the elements of the domain and the codomain. Okay, so that then is the interpretation of what it actually means to conjugate one element of the symmetric group of the set of n elements by another element of the symmetric group on the set of n elements. Okay, right, so we'll have a break here, and then we'll make a few final comments in the final video.